In this video, we're looking at electromagnetic induction, and we're talking about Faraday's law in particular. So the science understanding for today, straight from the outcomes, is talking about Faraday's law, what it is, and explaining how we get to and how we use this EMF formula. So Faraday's law of induction states that a changing magnetic field will induce an EMF in a loop of wire. Faraday concluded that the induced EMF, the electromotive force, is equal to the rate of change in magnetic flux. This is known as Faraday's law of induction, and it's defined as the change in flux, delta phi, remember that this is the flux, divided by the change in time. So the rate of flux changing per unit of time is equal to the induced EMF. Sometimes you'll see that this is shown as a negative, and the negative just symbolizes that it's in the opposite direction, or it's opposing the action that's happening, which we'll cover when we talk about what Lenz's law is. But for now, we will generally use this notation. So to break it down, the EMF is the electromotive force, and that uses the symbol of V for volts. The delta phi is the change in magnetic flux, which remember from the last video is the units of Webers, WB, and delta T is the time over which the magnetic flux is actually changing, so that's in seconds. So the Faraday's law can be applied to a situation involving multiple, say, n number of conducting loops. Rather than just a single loop, we can have lots of them, and we use the symbol n to denote how many loops we have. This would be an example of the solenoid that we've seen earlier in the electric section. In this multi-loop solenoid version, we just multiply each EMF per loop by the number of loops. So if we take this formula for EMF of one loop, we just multiply it by n number of loops, and we get the average or general EMF formula where n number of loops times delta phi equals delta t, divided by delta t. This should be denoted as a capital. You can use both. Sometimes I use lowercase for n, sometimes use capital, but as long as you know that it's representing the number of loops. Just a side note on the EMF and the flux is the number of lines passing through an area in a certain time. If you remember, we talked about it's kind of like the area is your net, and the number of magnetic lines that pass through that net are kind of like the fish that you catch in it, and that's what we're defining. The flux is the number of fish in a certain amount of time. So from this, if we change the flux, and therefore we're changing the EMF, then we can actually do this in a couple of different ways. Firstly, when a straight conductor moves in a magnetic field, as we outlined earlier. So when that conductor is moving through a magnetic field, it generates this force by pushing the electrons to one end of the conductor and inducing charges. The area of the conducting loop may change due to its shape. So if the EMF is n number of terms times delta phi over delta t, then we could break this into, remember from the formula for flux, it's the magnetic field strength, the change in area over the change in time. So if we change the area of our net, of this loop, then the flux is going to change, the EMF is going to change. If we move the conducting loop in or out of the magnetic field, that's going to affect it, because we've now got a moving conductor. When the area is constant but the magnetic field strength itself is changing, again we can rearrange our formula, and we had delta phi, so if area is constant but the magnetic field strength is changing, we get B2 minus B1. So constant, changing this results in a changing EMF due to a change in flux. So we can rearrange whether A is being changed or B is being changed, and in both cases we change the flux value. Therefore, if flux is changing, we're changing the EMF. This is a great little recap. So in my opinion, Doc Physics is one of the greatest YouTubers out there in terms of physics. So I spent a lot of time at uni watching his videos to help get through revision and explain concepts. And in his explanation, he does use some higher level mathematics than what we actually use. So he'll refer to dot products, which explains why we have the cos theta in the formula, as well as referring to the EMF as a derivative. So there is a lot of really good, really powerful mathematics with dot products and calculating derivatives and things like that explain really in depth how we get these formulas. So if you get lost a little bit with some of the maths that he goes through, don't worry, you're not expected to understand that. This is more of a university maths version of explaining the same concept.
So if you have kids, it's inevitable they're going to come up to you and say something like, "Daddy, why is there rock and roll and you're going to say to them, rock and roll comes from Faraday's effect of electromagnetic induction. And it's like this. It's like if you have a hunk of metal, and this is really just going to help us transfer flux from one place to another. And, oh, we should label this. It's not just any metal, but let's say that it's a ferrous metal. It's got to be magnetizable, but we probably don't want it to be very magnetizable. It's just going to be a little bit magnetizable. And I'm going to put a switch in the circuit here and have the circuit go through battery. And then I'm going to have the circuit go through a resistor just to show the fact that every circuit has a resistor. That's fine. And then I'm going to have it go whoop, in front and then back around, and 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 then it will be leaving to that switch right there. You get the idea here? It is looping around that piece of metal. And then I got to have this other one. And this other one's going to be doing the same thing. Let's go with a different color. Why the heck not, right? So there's another coil here. It goes in front and then back around, in front and back around, in front and back around. Let's not bicker about number of times around or anything like that yet. And all I'm going to put over here is a voltmeter. Probably going to be a really sensitive voltmeter, probably a galvanometer. But in this case, we got the same number of coils. N is equal to 4 here. And what I want you to believe is that if I create a magnetic field inside of this coil by flipping that switch, close the switch, the battery makes a current go this direction, which makes a magnetic field, well, let's figure it out. It's going that way. It makes a magnetic field pointing this direction inside the coil. But inside this coil, inside this solenoid, there's metal, and the metal then magnetizes, which tends to magnetize a little bit more of the metal, and a little bit more of the metal, and a little bit more of the metal. So in general, this whole piece of metal will become an electromagnet during the time that the current is flowing. So if I do close the switch, it will magnetize the piece of metal, and this will be the North Pole, and that will be the South Pole. Let's see if we can label that sucker right there. North Pole, South Pole, and then the beautiful thing is, here's the most beautiful thing. Since the magnetic field inside of this coil changed, the coil induces a voltage, and that voltage can be read off by this voltmeter right here. That is Faraday's law of electromagnetic induction. And Michael Faraday is one of the we'll go Spanish flavor. He's one of the physicists who sought symmetry because he knew that a current could make a magnetic field. He was wondering if a magnetic field could make a current, and he found that most definitely it could. There will be a steady current through this voltmeter. If it's, well, you want to put a resistor there? Let's put a resistor in here. There will be a steady current through that resistor if we have, wait a second, is that right? No. There will be a temporary current through that resistor if we create a steady current through this resistor. Woo, interesting. So there's something more complicated going on here. We need to go a little bit further. Let's define magnetic flux first. We'll probably see that what am I talking about? Les Paul and his electric guitar that he invented were, I think, at the very basis of the ability to make rock and roll, and Les Paul sort of made that awesome, and Jimi Hendrix brought it to fruition. So what I want to do next is define flux. This is magnetic flux. Looks like electric flux, doesn't it? So this is the Greek letter phi with capital, and so phi is related to flux because it's flowing something or other. But flux is just field dotted into area. It's the field that goes through a particular loop. So it's just going to be B times A times cosine of the angle between. But the angle between, I need to get my loop. Hang on, right there. You need to remember that a loop's direction is outward for the loop. That loop right there has it has a direction. The surface itself has a direction that is out from it. How do you tell out from in? very carefully. You probably are not going to be able to tell unless you know which direction the current is going. So we're going to define direction in a little bit, but we're saying that this is the definition of flux, and it has a dot product, which is also called the scalar product. Because it does not give a vector. Notice that flux is not a vector. It's simply a quantity, and it has units. I would say that the units of flux, well, the units of flux have to be the unit of magnetic field, so that's Tesla, and then the units of area is meter squared. Tesla per meter squared is called a Weber, or WB. That's kind of cool for Webster, all right. But here's my point. Magnetic flux as defined is not particularly interesting, but I need to give you Faraday's law of magnetic induction. And Faraday's law of magnetic induction says that an induced voltage is caused by a change in magnetic flux. If magnetic flux changes, then you're going to get an effort on the part of the coil that's experiencing the flux changing. Like, here's the idea. The idea is, if I've got no magnetic field going through here, and then I turn on a magnetic field through here, then the loop's not going to like that, and it's going to get a voltage that will try to oppose that. And I'll go into a little bit more detail about this minus sign right here. But the minus sign says nature hates change. Let's just define that little very carefully here. All right, this is actually my favorite part of this entire law, but the next part says that if you've got more loops, then you get a greater induced voltage. I think that sort of makes sense. A single loop doesn't have a lot of induced voltage, but if you get a heck of a solenoid, then you have a great induced voltage. And we also want to say that this is change in flux over change in time. And let's quit screwing around. I mean, you could go all formal on this. You could say negative n times flux final minus flux initial divided by T final minus T initial. Oh, we're using noughts in this here. Sorry. All right. You could do that, but let's be honest and just say that we're actually talking about the derivative. It will actually be negative n times d phi dt. As flux changes, a voltage is induced. And a lot of books like to put this as the EMF, but you know that I hate that. I don't like that. It's just a silly notation thing. An induced voltage occurs, and the faster flux changes, the greater the induced voltage is. That's awesome.
All right, so a practice question for you using this concept. So we've got a square loop of wire. They give you the dimensions. You know the strength of the magnetic field. Calculate the change in magnetic flux through the loop, and also calculate the EMF induced within the loop.
I see a sense of wonder deep inside your eyes as we're sparkling and twirling in the twilight. And after 3 long years, I think that we both need this. So we seal the deal in the parking lot with a kiss.
So the first question, we end up with a -3 times 10 to the minus 2 Webers. And in the second example, the induced EMF uses the change in phi, the change in flux, over the change in time. We end up with -2 times 10 to the minus 2 volts. All right, part 2. Again, we've got a changing shape. The original square is moved in the right in a time of 1.5 seconds, so that only half the area of the loop remains in the magnetic field, and it's still a 3 Tesla magnetic field. So calculate the flux, calculate the induced EMF now, and then we've got a similar context using a solenoid, knowing the number of turns. So have a go at these ones.
With the notes ringing in my head, let the rain fill my mouth, and in a couple of hours I'll be dead. But all the while my lips are whistling a tune, but the beauty lies in how you will revive me.
So part I, we end up with negative 6 times 10 to the minus 2 Webers. The induced EMF is negative 4 times 10 to the minus 2 volts. And in the solenoid case, we end up with 0.44 Webers and an EMF of 0.59 volts. So from here, have a look at the workbook questions on page 219. Question 529 addresses this concept of the changing EMF and the kind of questions that we've just seen. There's also a really good FET simulator. So there are links to that within our course. You can just type in Faraday's law FET, P-H-E-T, online, and you'll find it, and it looks a bit like this. So you can move a magnet in and out of a coil of wire, and you'll see it inducing a voltage here. The light bulb will go up, and it'll give you a sign of the charge that you're producing. So whether it's traveling in that direction or that direction, you can change the number of coils, flip the magnet, things like that. So it's a really good simulator of this concept of Faraday's law.